sketch and compare f of x equals to x cubed, g of x equals to 5x cubed, and h of x equals to 1/5 x cubed. We're now looking at dilation of a cubic. Remember, dilation is the effect of stretching or compressing our graph away from an axis. In our situation, when you put a coefficient in front of the x cubed term, that's called the dilation factor. And when you put that coefficient there, what happens is the graph is dilated by a factor of a, by that dilation factor, away from the x-axis. And the reason it's away from the x-axis is because you can imagine, say I have the same x value in all of these points. What happens is the original graph has the x value here. Let's say this is the x value of 1. And then if I multiply a times x cubed, I'm multiplying that y value by a. So if a is larger than 1, it's going to shoot upwards to whatever is a times 1, which is a. So it's going to stretch from the original position, which was here. It gets stretched upwards away from the x-axis. And if a is between 0 and 1, our original point was like here, and it gets compressed, it gets sucked back towards the x-axis to turn into the a coordinate here, but now a is a fraction value, okay? So you can imagine that whenever you multiply your cubic by a, whether if a is a large number, it's going to stretch all the y values away from x-axis. And if a is a small number, it's going to pull all of those y values closer towards the x-axis and make it a little bit flatter. The effect that has overall on the diagram is you can have a look and see, compared to the normal base graph, when you have a is a large number, larger than 1, your graph appears narrower because you can literally imagine it being stretched up and down, and it becomes a bit narrower than before. And if you have a is between 0 and 1, the opposite happens, where because the graph is being pushed down towards the x-axis, it appears wider. Okay, but we're gonna actually go through an example of this and see how it looks in terms of the calculations. Now, once again, I'm going to fill in this table and then compare the coordinates and draw all three of these graphs this time on our axes. I'll quickly go through f of x is cubed, so I'm going to just cube these. -3 cubed is -27, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 8 and 27. Now for g, all I'm doing is multiplying my cubed. The only difference is I'm multiplying my cubed by 5. So I'm going to go through and multiply each of these by 5. -27 times 5 is equal to -135. -8 times 5 is -40. -1 times 5 is -5. And then I have 0, 5, 40, and again 135. Now for h of x, I'm going to multiply it by 1/5. So I'm going to go here and multiply by 1/5 compared to the original graph of f of x. Starting with -27, multiplying that by 1/5 is the same as dividing by 5, and there are no common factors, so I have to leave it as a fraction. Same with the 8, the 1, 0 divided by 5 is still 0, and then the same thing happens on the other side. 8/5 and 27/5. Right, so I found all of my coordinates. I'm going to erase this so it's not over my axes. And let's just start trying to draw them. I'll draw out my f of x graph. All of them go through the origin, so that's important to label. And so for f of x, we'll have 1, 1, then 2, 8, and 3, 27, which is quite high up. And the opposite of that down here, -1, -1, -2, -8, and -3, -27, which is quite low. Connecting those with a bit of a curve, it's not bad. This is f of x, and that's the original graph, x cubed. Now g of x, is crazily stretched compared to this. If I start with, I'll start with 0, 0, but then I go across by 1. I have 1 and 5. So 1 and 5 is about here. And then it goes to 240, which is way above what I've even got here. So I can't even really draw it very well, but it's going to go very, very high and kind of like that. So imagine if my axis extended up there somewhere, I would have 40, and then the next one across for 3, this one would line up with 135, so it's very, very high up. And for negative numbers, it does the same. So at -1, it's already at -5, and then it goes all the way down to -40. So I won't be able to draw that coordinate in, but I can imagine it's going to really keep going, and it's going to be very, very steep for g of x. I'll label that one. That's g of x equals to 5x cubed. So you'll notice that because I had a number here that's larger than 1, it scaled everything by multiplying it by 5. So every coordinate got pushed up 5 times as high, stretched away from the x-axis, and overall the graph appears to be narrower. Now for h of x, we're going to go through and every point turns into 1/5 as high. So for the coordinate at 1, instead of being at 1, 1, it's now at 1, 1/5, which is a lot closer to the x-axis. For 2, it's instead of 8, it's 8/5, which is a little bit under 2, so it's maybe here. And then for 3, we have 27/5, which is just a little bit more than 5, so it might be just here. So now you'll see our graph looks a bit wider. This is the graph of h of x. It's a little bit wider than our original graph. It's going to have the same shape going on over here, a little bit wider. Our h of x graph was pulled down towards the x-axis, and that's what made it wider, because all of our y values are now a bit smaller, and our graph takes longer to get up to the same values. And for g of x, because we were multiplied by a larger number than 1, we were stretched upwards. All of our values were pushed up by quite a lot. As a result, our graph got narrower. Okay, so that's how you can interpret your dilations for a cubic graph.